This is an extension of the book example 11.2.4, which only discussed the eigenvectors and eigenvalues in an abstract sense, toward a more concrete example of what you would use the eigenvectors and eigenvalues for. And so if you remember in example 11.2.4, there was a Markov process that described the populations of Delaware, Maryland, and Pennsylvania. So the new populations, the Markov matrix here in this case was 72%, 12%, 10%, 20%, 78%, 3%, 8%, 10%, and 87%. Okay, and the year-to-year dynamics followed this linear combination. So the next year, the populations would be a linear combination of the previous year. Since this matrix is a Markov matrix and every column adds to 1, that means that the total populations will be preserved. So we're only shuffling people around, we're not creating people. So we convinced ourselves last time that the eigenvalues, Markov matrix will always have an eigenvalue equal to 1. And the eigenvector for that eigenvalue was 0.56, negative 0.56, negative 0.62, negative 0.82. Another eigenvalue was 0.77, and the associated eigenvector was minus 0.09, minus 0.70, and 0.79, and the last eigenvalue was 0.60, and the associated eigenvector was minus 0.62, 0.70, and minus 0.07. And we convinced ourselves that in general, we could always write if we express the population in terms of a combination of the eigenvectors at any one year, we could advance simply by taking the eigenvalue to some power. So if I write dmp at year 0, if I write the initial population in terms of the eigenvectors, so I'll write that as a linear combination of the eigenvectors. Then we convinced ourselves that the population at year n, which was just going to be what you get when you take that initial vector and multiply n times by that M matrix. That M matrix would be acting on the linear combination of the eigenvectors. And that would just give us alpha 1, 1 to the n, E1, plus alpha 2, lambda 2 to the n, E2, plus alpha 3, lambda 3 to the n, E3. Okay, so now suppose, this is a very general setup, suppose we want to use it to solve the problem that initially everyone is in Delaware. Please insert your favorite joke there about everyone being in Delaware. So the initial population would be 1. Let me write that as D M P 0 be 1 0 0. So now our main goal, so this is a very general expression we have here for the population vector at any other time, but we still have to find the initial population expressed in terms of the alpha 1, alpha 2. I'm sorry, I guess it would be better to circle these guys. We find the initial population expressed in terms of alpha 1, alpha 2, and alpha 3, and that will be a linear algebra problem. Okay, so we have to now solve for alpha 1, E1, plus alpha 2, E2, plus alpha 3 E3. And this is a meat and potatoes problem from chapter 9, where we're trying to write some linear combination of vectors, which adds up to a given vector. And as we know from chapter 9, the right way to do that is by using Gaussian elimination. So I can write that in matrix form, and I'm going to take our three eigenvectors, E1, E2, E3. Each of those becomes a column. And remember, matrix multiplication is like taking linear combinations of the columns. So my matrix I'm trying to solve, E1 is minus 0.56, minus 0.62, minus 0.82. E2 is minus 0.09, minus 0.70, positive 0.70, and finally E3 is minus 0.82, positive 0.79, and minus 0.07. And if you look, all I've done is really taken these three guys and treated them as column vectors, and then I am multiplying by alpha 1, alpha 2, alpha 3. Okay, that's my linear combination of the vectors E1, E2, and E3, and those guys are supposed to add up to the initial population 1, 0, 0. Okay, so all I'm doing here, I'm writing the linear algebra problem, which is challenging me to write the initial population in terms of the eigenvectors, and so I can row reduced echelon form of the auxiliary matrix. We know that this matrix will, since those vectors are independent of each other, that matrix will not be singular, and the inverse inverse will exist, and the solution to this equation will be unique. And I plug that into my favorite tool, and it tells me after I get it into row reduced echelon form, well, I'll just write the matrix in row reduced echelon form. Since it's non-singular, it has to be, we knew it had to look something like that, and it turns out that alpha 1 is equal to negative 0.4304 ... alpha 2 is equal to minus 0.59026 ... and alpha 3 is equal to minus 0.8608 ... Okay, so now what have I done so far? I've succeeded in writing my initial state in terms of the eigenvectors. And then once I have my initial state written in terms of the eigenvectors, this is the answer forever and ever. So the population in an arbitrary year, so D, M, P, in the nth year will be alpha 1, which is minus 0.43, etc., times 1 to the n, also known as 1. So I'll just remove that. E1, and alpha 2 is negative 0.59, ... and then I have lambda 2, second eigenvalue, which is 0.77, and I have to raise that to the nth power, times E2, and then finally I have my alpha 3, which is the negative 0.8608 something, and then I need lambda 3, the third eigenvalue, which is 0.6, and I need to raise that to the nth power, 0.60 to the nth power, E3. Okay, and so for instance, if I want to know what the population is after 100 years, we could all be dead, the United States may no longer exist, but let's suppose that Delaware, Maryland, and Pennsylvania do. So after 100 years, DMP 100 will be negative 0.43 ... times E1 plus minus 0.59. Then I have 0.77 to the 100, so let me just bring that up conveniently. Mathematically, 0.77 to the power of 100, and that's 4 times 10 to the minus 12. 4 times 10 to the minus 12. And so that is effectively 0. And then we have minus 0.8608, ... and then I have 0.60 to the 100 because we're waiting 100 years, and that is going to be even smaller, a lot smaller, so that's turns out to be 10 to the minus 23. We're talking Avogadro's number is small, so that's 6.5 times 10 to the minus 23, teeny. This was times E2, was times E1, E3. So this just shows you that the population really becomes quickly dominated for eigenvalues that are smaller than 1, really becomes dominated by the eigenvector that has a magnitude bigger than 1, and so that should just give me the essentially if we go through and we take minus 0.43 times my original E1 eigenvector, the minus 0.56, minus 0.62, minus 0.82, we'll see that we get something that adds up to 1, but has the appropriate ratio of the columns in terms of the ratio of Delaware to Maryland, Maryland to Pennsylvania, and Pennsylvania to Delaware. So that is an example of where it is convenient to use the eigenvector and eigenvalue decomposition of the population, because the evolution, when you write it in terms of the eigenvectors and eigenvalues, is drop dead simple. You just take each eigenvector, and each eigenvector evolves just by getting another power of the eigenvalue attached to it. So the E2 component just gets another factor of lambda 2 multiplied to it every time the year passes, and the same thing with the E3 component just gets one more factor of lambda 3 every time a new year goes by. So this is why it's very convenient to use the eigenvectors and eigenvalues to analyze the populations in Markov processes.